Hello, welcome to Sigma Maths. This is the second video in a series covering the exponentials and logarithms content of the Maths A-level. In the first video, we had a detailed look at exponential graphs, the special case of e to the x, and the gradient function of e to the x. In this video, we're going to be looking at a variety of practice questions based on the same content. So, for our first 5 questions, we have got 5 exponential equations written down here, and what I would like you to do is pause the video and have a go at sketching each of these equations, showing all interesting features of the graph on your sketch. So by interesting features I mean all intersections with the axes and anything else that exponential graphs usually have. Okay, so now that you have had a go at this yourself, let's go through this together. So question 1, y equals 3 to the x. Straight away, we notice it's exponential. We're thinking, is the base number greater than 1 or less than 1? Because that's going to determine whether it goes up from the left or comes down from the left, so whether it's increasing or a decreasing function. 3 is most definitely larger than 1, so we know we're having this kind of shape. It does not have any transformations attached to it. It is just in the form a to the x, so that we know we can just use that shape. Always try and do it in one swift movement like this. And remember, we do have to mark on our intersections. Now, if you remember, all the intersections with the exponential graphs when they haven't been transformed are always 0, 1, because anything to the power of 0 is 1. And we're just making sure that the left-hand side of this graph, the bit here that tends down towards the asymptote, is always looking like it's getting closer to the x-axis, never quite touching, and not coming back up away from it. So there we go, we're always going to label our graphs y equals 3 to the x. Lovely. Now, in terms of labeling our asymptote, we could just make a note here, y equals 0. Asymptote not necessarily required because it is already on the x-axis, but if you want to be very clear to the examiner that you know what you're doing, it might be worth writing that down. Okay, question 2, y equals 2 times 5 to the x. So again, 5 is greater than 1, so our exponential function is definitely an increasing one with that same kind of shape as the last one. But we now have a 2 times outside the function, so we're seeing this as a 2 f of x transformation. We know this is a stretch in the y direction. In terms of how the graph looks on a sketch, it's not going to look particularly different. Only if it was on the same set of axes as the original function would we see a massive difference. So it's still going to have exactly the same shape. So I'm just going to draw that now. And it's the intersection point that's going to be different. So we should always maybe do a quick calculation just to make sure we know we're right. So we're looking at when x equals 0, 2 times 5 to the 0, that's 2 times 1, which is just 2. So this time, because it's a transformed exponential function, we are having the intersection point 0, 2, and an asymptote of y equals 0. Good. Okay, question 3. Y equals 3 to the x minus 2. Again, this is a transformation of a exponential function with base greater than 1, so still going to have that same shape. We're looking at transformation of the form f of x minus 2. So we're remembering that that is a translation by the vector 2, 0 inside the function, does the opposite to what you'd expect. So again, if you just picture an exponential graph already drawn, it's going to shift it 2 units to the right. That's actually not going to look that much different when it's shifted, seeing as this is a sketch and we don't have a scale. So again, we can draw similar kind of shape. But we are going to want to make sure we work out what that intersection point is there. So again, a little bit of working. Always show your working. In the exams, you never know what marks you might be able to get. When x equals 0, y equals 3 to the 0 minus 2. So we're looking at 3 to the negative 2, which is 1 over 3 squared, therefore 1 over 9. Okay, so we've got the point 0, 1 over 9. Brilliant. Oh, y equals 0 asymptote. Okay, question 4. Right, a third to the x. So straight away we're noticing that a third is less than 1. So we've got our flipped around exponential function that's reflected in the y-axis. So rather than going along and up, it's going to come down and then along into that asymptote. So I always find these slightly harder to draw. Whether you want to come down and draw it or come up from the left kind of depends on what works better for you. Clearly not that way for me. Particularly hard to do on the computer as well. So there we go. Just about managed the right kind of shape there. Okay, intersection point then. So again, it is just a standard exponential function. This one doesn't have any transformations. So it is just our 0, 1, and the same asymptote that we had before. Okay, last one, question 5. Got two things going on here. We've got the fact that our base number is less than 1, so it's going to have the same shape as the last one. But then we've also got this plus 4. So we've got a transformation outside the function of plus 4. That's going to be a translation again of 0 and 4 this time because it's outside the function, so it's affecting y values. So something a little bit more interesting happening here in that we need to redraw our asymptote because it has moved as well, because it's the y values being affected. So our asymptote is normally y equals 0. We're going up by 4 units. Therefore, our new asymptote is going to be up here, y equals 4. And we can draw the shape. We know that it's going to come down from the left, so I'm going to draw it up from this way because it just works a little bit better for me. There we go. And in terms of where it crosses, well, if this hadn't been shifted by plus 4, then it would be sitting down on the x-axis here, and then it would pass through 0, 1. So if we add 4 to that, we're going to get 0, 5. You can always put the value in to check. X equals 0, y equals a quarter to the 0, which is 1, plus 4, which is 5, just to confirm. Okay, so there we go, 5 sketches. Hopefully that went well for you. If not, then make sure that you look back through the video there and understand what went wrong and why. Okay, next question. So this is a question about the function, the exponential function, without the need to sketch a graph or look at a graph. In fact, we are using information about the points that this graph passes through in order to answer the question. So we've got our function here, y equals ab to the x. Make sure you realize that is a times b to the x. That power of x is not affecting the a. And we are told we are going through points 1, 15 and 4, 405. So what we have here basically are pairs of x and y coordinates that we know must satisfy the equation, otherwise they wouldn't be points that lied on the equation. So seeing as they satisfy it, we're going to substitute them in so that we can come up with some equations in the two unknowns a and b, because that's what we're trying to find here, a and b. So let's start with I'm going to label these points so to clear my working what I'm doing. 1, 2. Point 1, so we're going to have 15 equals a times b to the 1, so it's just 15 equals ab. And point 2, we're going to have 405 equals a times b to the 4. Okay, so we have got a pair of simultaneous equations. They are not linear simultaneous equations though, however, so you cannot stick them into your calculator, I'm afraid. But there is an easy way of dealing with these, or we can either do substitution, or we can notice that much like with linear simultaneous equations, we could add or subtract to eliminate a variable. Here we can divide because we've got a to the 1 in both, so we can take our larger equation. So I'm going to use the labels for the points as labels for the equation. So if we take the larger one and divide it by the smaller one, then we're going to have 405 divided by 15 on one side, and then a times b to the 4 over a times b on the other side. And what's nice about that is that the a's cancel out. So 405 divided by 15 is 27. B to the 4 divided by b is b cubed. This is a good sign. It is working out nicely. Cube root both sides. We get b equals 3. Once we have one of our unknowns, we can go back to probably the equation with the smaller numbers in it. So 15 equals ab, but now we know b is 3. And then we can simply divide both sides by 3 to get a is 5. So there we go, we've worked out our values. We can stop there, that's all the question was asking for. It's always nice to rewrite the exponential function that we were finding in this question. There we go. Y equals 5 times 3 to the power of x. Good. Okay. Next question. We've got a very similar one. We've got points here, we've got negatives, and we've got fractions going on, so this is going to be a little bit trickier. And we've got a slightly different question to begin with as well here. By drawing a sketch of this function, explain why b is between 0 and 1. Okay, so a bit of sketching here. Now, we cannot draw a sketch entirely on this information. We don't know anything about a and b. We know it has an exponential shape. We don't know which way it's going. So we are using these points to draw a sketch. So I'm just going to do a set of axes. There we go. Y, x. Okay, so we've got a point minus 218. Now it is just a sketch. We don't need to worry too much about the scale, but we do want to put them roughly in the right place. So minus 218 could be something like up here. And then 3 and 2 over 27. So we're going a bit further away from the x-axis in the positive direction, and a very small value over here. Now we know what kind of shape. This either has this shape, or it comes down and has a shape like this. Now clearly, looking at where these points are, it's impossible for it to have the first one, so it's not that kind of shape. It's the ones that come down, ones that I find just a little bit harder to draw. So we'll go like this. And explain why. Well, b is between 0 and 1 because as x increases, y decreases. Okay, that's how you know that your base number is between 0 and 1. If y increases as x increases, then you know you've got a base number greater than 1, less than 1 if you have this kind of inverse effect happening. As one increases, the other decreases. Alright, part B, from algebra again, much like the last question, so we'll jump straight into that. We've got 18 equals a times b to the negative 2. That's point 1. Point 2, let's label them quickly, 1, 2. We've got 2 over 27 equals a times b to the power of 3. Okay, so we could do division again like last time, but I figured we'd use a slightly different method this time just to expose you to as many different ways of doing things as possible. And we will do substitution method here. So that requires rearranging one of the equations to make the chosen variable the subject. I'm going to suggest we make a the subject here. So if we take this first equation, so consider that that's 18 equals a over b squared, if we just dealt with that negative power, negative 2 there, then actually that's quite easy to rearrange to make a the subject, because we just need to bring the b squared up to the other side, so 18b squared, and that's ready then to substitute in to equation 2. So we just draw a little arrow here. So if we put that into equation 2, we're going to have 2 over 27 equals a is now 18b squared, so we've replaced the a here, times b cubed. Okay, so we're going to see if we can always look for any simplifying that you can do to an equation before you reach for your calculator. I know it's very easy to put these things into the calculator and not have to worry about the fractions and everything, but one, you'll be more confident, 2, you'll work more quickly, and 3, you'll be better at your algebra if you just get yourself to do as much of the maths in your head or with written methods rather than always reaching for your calculator. So looking here, what can we do? We can cancel the 2 and the 18 down to 1 and 9. And then we're going to need to bring that 9 down. We're going to have a b to the 5 left over here from the b squared and the b cubed. And we're going to have a 1 over 27 times 9. Now, quite often these questions work out to be reasonably nice numbers. So knowing that it's likely to come out as you know, like here's a power of 5, we're probably going to be able to do the fifth root of this number. We notice that 27 is 3 cubed and 9 is 3 squared. So actually that fraction can be written, I'm just going to bring myself up here, as b to the 5 equals 1 over 3 to the 5. Okay, we haven't touched our calculators at all here, we're just noticing we've got a square and a cube of 3 here. This all works very nicely because now when we do the fifth root, we just get a third. Okay, so find the values of a and b. We've got b, we just need to go back and find a. We already rearranged one of the equations to make them a equals. So So that's nice and easy to do. 18 times a third squared. So that's 18 times 1 over 9. It's 18 divided by 9, which is 2. So we've got our two answers there. We can write out the function. It is 2 times, and then a third to the power of x. Don't ever try and combine the 2 and the third together. So don't make it 2/3 to the power of x, for example. They cannot be combined because the 2 is not being raised to the power of x. So that's that one finished. Okay. Right. Next question. So here we have got a set of 3 graphs, each with some information, but not the equation of the graph. And we are told that each graph has the equation of the form y equals a e to the bx plus c, and then we are then asked to find the value of a and c, and just to state whether b is positive or negative. That probably means that we don't have enough information to work out what b is, but bearing in mind that that is the number in front of x, that's going to be us thinking about whether it is just a standard exponential graph, or if we remember what negative inside the function does, whether it's a reflection in the y-axis. Yeah, inside the function affects x values, therefore it's flipping in the y-axis. Okay, so let's jump in with what we can do. So let's call this part A, do the working for it underneath. So information that we've got here, we've got an asymptote of y equals 4, and we have got an intersection point of 5. And we've obviously got our standard equation a e to the bx plus c. Okay, so we're going to need to use the intersection point and the asymptote to work out what's going on. Now the plus c, that's clearly going to do some kind of shifting of the exponential graph, like a transformation, and therefore our c, just through that knowledge, must be 4. Okay, so that brings us to y equals a e to the bx plus 4, and then we use our point 0, 5, sub those values into the equation, so 5 equals a e to the 0 plus 4, so 5 equals a plus 4. That tells us that a must be 1. So we found our value of c, found our value of a. Is b positive or negative? Well, it has the standard exponential shape. As x increases, y increases, so b must therefore be positive. Okay, part B. So let's have a look here. Again, where the asymptote is tells us what the value of c must be, because that's the only way that the asymptote can be moved around. So straight away we can go with c equals minus 5. And then we've got our intersection point there of 0, 3, so we can put that point in. 3 equals a e to the 0 minus 5. Okay, so a therefore must be 8, because e to the 0 is 1, and we're adding the 5 over to the other side. So we've got our a, we've got our c, and then we are just stating whether b is positive or negative. So this time it is coming down, and as x increases, y decreases, so that must mean b is negative, because it's like we've flipped the original shape around in the y-axis. Good. Okay, part C. So again, 5 over 2, c must be 5 over 2, and we have a point 0, 4, so we'll substitute this in. 4 equals a e to the 0 plus 5 over 2, so a therefore is going to be 4 minus 5 over 2, so that's 8 over 2 minus 5 over 2, which is 3 over 2. There's our a value. Just having a look, as x increases, y increases, therefore b is positive. Okay, there we go. We've used the information about the intersection point and the asymptote to fill in some of the missing information from the equation of these graphs. That's part C there. Alright. Okay, question 5. We're almost there. We've got 2 more questions to go. Right, this one is a differentiate. So this is using our formula for differentiating anything of the form y equals e to the kx. Okay, so I'll just give you a second to pause, have a go at this yourself. Now I'll remind you that the formula is, remember we mentioned the chain rule in the first video, you're not doing the whole bringing the power down and taking from the power here. We are bringing the exponential function differentiates to itself, that's why it's so special, and then you times by the derivative of what's inside the function, and the derivative of kx is just k, so the k comes down in front of the exponential. Nothing changes about the exponential. Do not be tempted to take one away. So let's have a look here. So dy by dx equals, so here e to the 5x becomes 5e to the 5x, and then here again, so we've got a 4 in front of the e at the moment, so the negative 2 is going to come down and make that minus 8e to the minus 2x. Okay, that's it. Part B, now this one, currently written as a product, we don't until next year, in year 2, have a way of dealing with products in differentiation, so we're going to have to rewrite this equation so we have separate terms, and that's just going to require a bit of expanding out. So e to the 3x times e to the x is e to the 4x minus 3e to the 3x. Now we can differentiate. Make sure that you don't just put another equal sign and carry on. Y is not equal to dy dx, so you're going to have to relabel the line that you're working on here. Okay, so here k is 4, so the 4 comes down because it is the differential of 4x, and then we get e to the 4x back because that's just the way the exponential function works in differentiation. And then the 3 is going to come down here to make this 9e to the 3x. And that's it. It's a bit of differentiation practice. Okay, last question. Consider the curve given by y equals e to the 0.25x. X belongs to reals. Okay, so if you haven't seen that before, I imagine you have, but just in case, this means literally x belongs to the group of real numbers. Real numbers. That just means all the numbers that you're used to, rational and irrational, fractions, negative, integers, all of them. It just means that there's no restriction on the numbers that can go into this. Show that the tangent to this curve at 4e goes through the origin. Okay, so if we want to show that a straight line goes through the origin, it would be helpful to have the equation of that straight line. In order to find the equation of the straight line, we need to find the gradient of the curve, because we know definition of a tangent is that it has the same gradient as the curve at that particular point. So we're going to start off by writing down dy by dx. 0.25 comes down, because it's the differential of 0.25x, e to the 0.25x. Okay, and then this is the gradient at any point along the curve. We want the gradient at this point here, when x is 4 and y is e. So what I tend to do is put this line down here and say x equals 4, and that basically says I'm going to evaluate this expression at the value of x equals 4. So that's 0.25 e to the 0.25 times 4, which is just 1. So you probably write that as 0.25. Oh, 0.25 e. Okay, just going to get rid of that. Okay, so we've got our gradient. This is m, so I'm just going to get rid of that and put m equals. Now we're going to use the fact that we have the gradient and a point, along with the formula y minus y1 equals mx minus x1. Should be a well-known formula to you from an earlier chapter, coordinate geometry. So we're going to put y minus e equals m, which is 0.25e times x minus 4. Okay, so let's expand that out. Y minus e equals a 0.25ex minus e, because 0.25 lots times 4 is just 1. So we just got a minus e. Now straight away we can see the minus e and minus e are going to cancel out, so we can put a line through those, and we are left just with y equals 0.25ex, and we are trying to show that it goes through the origin. So if we put x equals 0, we get y equals 0.25e times 0, which is 0. Therefore, just make a little conclusion here, tangent passes through 0, 0. We have shown what they have asked for. Make sure you're very explicit in what you're doing. Communicate to the examiner well to make sure you get all of those lovely marks. Okay, so that's the end of the practice questions for 6.1 and 6.2 from the specification. This is just purely questions based on the exponential graphs, e to the x, various transformations of them, and then obviously these last two questions, a bit of differentiation or gradient function of e to the x. The next video in the series is going to be having a look at, or an introduction to logarithms and solving log and exponential equations, and then we will move on to things like modelling and linearization. Okay, thank you for watching. If you found it helpful, please click the like button, and don't forget to subscribe if you want to see more videos like this. See you in the next one. Bye.